So the second half of this course is integral calculus. So the first semester is all about the derivative. That was our calculus operation that we're focused on. Second semester is going to be focused on the integral, which is basically the inverse operation for the derivative. We touched on this a little teeny dipped our toe into at the very end of first semester when we talked about antiderivatives. We're going to kind of build that process out formally and give the geometric interpretation of kind of what this integral is. So to kind of as our dipping in, our starting point, we're going to start talking about calculating an area of something. Okay. Specifically, we're going to want to talk about how would we go about finding the area under a curve. So like the shape, say like we were looking at this shape S, we want to figure out the area of that shape. Now that's not trivial, and what makes that really a pretty difficult proposition geometrically, we have this one side that's all curvy, right? If that was just a straight side, no problemo, piece of cake, it's a trapezoid or whatever, like, or a rectangle, like, I gotcha. Easy formula. So let's kind of set aside something that's this complicated and look at something for a very specific f of x that's still curved, but something that, like, we'll use this as kind of our building up to how I would do this in generally for any f of x. And we're just going to pick a simple f of x, x squared. So we're going to be looking at calculating this area S. So back in geometry time, if you had like a figure like this that looked like the basketball key or whatever, how did we do something like this? Yeah, we broke it up into a couple of pieces, so we found the area of the rectangle plus half the area for the circle, right? We're going to kind of do that same idea here. So we're going to just divide this up into a bunch of different sections. Now, we'll talk about like how many sections we should use. For now, I'm just going to arbitrarily divide it into 4 sections. Now, as I divide that, what are these little sections starting to look more and more like? Each of those sections is starting to look more and more like a rectangle or a trapezoid, right? The smaller I make those, the more rectangular or trapezoidal they appear. Everybody agree with that? So what I can do is to find that area S. I broke it up into 4 subregions, S1, S2, S3, S4. And then I'm going to calculate the area of a rectangle that has the same dimensions as those 4 non-rectangles. So I'm going to call those rectangles R1, R2, R3, R4. So how would I write that area for R1? So what's the base? 1/4. And what's the height going to be? It's going to be the y coordinate for that point, right? Everybody agree with that? That'll be the same as the height for our rectangle, which would be f of 1/4. Everybody agree with that? Which is 1/4 squared, since our function was x squared. So that's R1. What's the area for R2 going to be? So it's going to still be 1/4, right? That's still going to be the base. Because it's still, we're going from 1/4 to 1/2. So that's still, the base is still 1/4. What's the height going to be? F of 1/2, which is just 1/2 squared, right? Because our function is x squared. What's the next one going to be? And then the last rectangle. So let's go ahead and compute that real quick. And I'm going to just skip the times 1 squared since 1 squared is 1 and that doesn't really mean anything. So I get about 0.46875. So that's my approximation. Everybody okay with that? Now, is this going to be an overestimate or an underestimate for the area S? That's going to be an overestimate, right? What if instead of using the rightmost point on my subinterval as the height of my rectangle, what if I used the leftmost point as the height of my rectangle? So, same idea. So you can compute it the same way. But again, I heard the mumbling already that what we have now is a underestimate. Let's see what that estimate is. Oops. Just pull that guy up. And that one is bye-bye. So 21,875. And again, already we see that's an underestimate. So using these two approximations, what can we immediately say about the value of S? It's in between those two. Exactly right. So everybody's happy there? Now suppose we used more rectangles. What do you think is going to happen with our approximation? It's going to get better, right? We have less hangover or underestimate. Let's go ahead and compute those real quick. So again, this is just me grinding through that same formula that we've been doing. Okay, so I have 0.3984375. And if I do from the left, I just swap that last term for a 0. Ooh, that doesn't seem right. What happened there? Should not have been bigger. What just happened? How did it get bigger when I deleted something out?
Because you're doing answer.
Oh, thank you for yes. Okay. Oh dear, I did not want to do that. And I just royally screwed up. Oh boy, all right. It doesn't matter anyways. Who cares, right? You're losing us, Mr. Kulik. It doesn't matter, right? Everybody gets the point. They got that bounds get tighter. So what if we use infinitely many rectangles? How would I calculate that? What's the height or what's the base of my rectangles? It's 1 over n, right? What's the height of that rectangle going to be then? 1 over n squared, okay? And then for the next rectangle, the base is 1 over n. What's the height going to be? 2 over n squared. Excellent. And we would do that all the way out. So we have that, right? So if I look at this, actually I'm going to leave this as, I think I'm going to write it as that. Be a little bit clearer where I'm going to go. Okay. Everybody still doing okay? So I notice that each term contains a factor of 1 over n cubed. Does anybody recognize this from Algebra 2? I don't remember. Some of you I had Algebra 2 with, but I don't remember how far did we get. Did we do sequences in series? If you had me with Algebra 2? Well, the honors course anyways. If you were in the regular course, we wouldn't have gotten that far. Enzo's looking at me like I don't remember that. Yeah, we wouldn't have gotten that far. Katie, Sienna, I think you were both had Algebra 2 with me, or at least part of the year. No? You had Morgan? Second semester is when we would have done that. Do you remember if we did this? We did? Okay, I thought we did. Anyways, there's a formula for this. Now, I would not expect any of you guys to remember what the formula is off the top of your head, other than like, I know there's a formula for this. Let me look this up. I'll write it down now. It's not something you'll need. Oops, that's a plus one. Again, not an expectation that you would have remembered that, but that is a formula, or the formula. As an aside, you know how we come up, or how you'd come up with this? So you'd have like the term number. So at 1, the output is 1. The sum of the first 2 terms is going to be 1 squared plus 4 squared, so that's 5. The sum of the first 3 terms is going to be 1 squared plus 2 squared plus 3 squared, so that's 14. You know, and you probably need a couple more, and then that's going to be 40. And then that one will be, 65? And that should be enough. So you look at the first common differences. Those are not constant. So we know it's not linear. You look at the second common difference. I guess I was going to need a couple more terms here. Those aren't constant, so I know it's not quadratic. But if I look at the third common difference, those are all the same. So I know it's cubic. So then what I would do is I'd write a general cubic equation. So like ax cubed plus bx squared plus cx plus d. That's my function. I have 4 coefficients to solve for, so I'd write a system of 4 equations. So that system would be, it would be like a plus b plus c plus d is equal to 1, where I plugged in the 0.11. And then for the next one, I'd have 8a plus 4b plus, that's supposed to be a 4, 2c plus d is equal to 5. That's me plugging in the 0.25. And I continue doing this, generating 4 equations. And then I would solve that system. What would be the easiest way to solve that system? As just a review from algebra. Yeah, a thing on your calculator is exact. Yeah, I would use a matrix and just use the RREF command to solve that. And you'll get the coefficients A, B, C, and D. If you factored those, you'd end up with what we're looking at right there. That's just as a quick review of how you could go about doing, how you'd come up with that formula on your own. Now, there's no guarantee that it would be polynomial, but the fact that you're talking about the sum of things squared should be, a sequence doesn't have to be polynomial. But if it's like the sum of stuff squared, it's usually a good bet that it'll be polynomial. Okay. Oops. I got this all jacked up now anyways, whatever. We'll sort it out later. All right. So we have that for r. So if I want then the limit as n goes to infinity of r, what's the problem? It's indeterminate, right? You have infinity over infinity. So what are we going to do? L'Hopital. So I'm going to FOIL the numerator out. Oops. I'll write it as like just. So that's going to be 2n cubed, and then plus 3n squared plus n. How many L'Hopitals are we going to need to use? 3, right? That'll get rid of the variables in the numerator and denominator. So again, I'm just going to kind of cut straight to the chase there. So the numerator will become 2 times 3 times 2 times 1. And the denominator will be 6 times 3 times 2 times 1. All of that stuff can reduce down to 1/3. Is that okay with everybody? Let's do that so it doesn't run together. So now we could do the same thing using like the other way of calculating our rectangles. We're using the left-hand side of our interval as the height of our rectangle. But guess what? What do you think the limit's going to be doing it the other way? This is the good part. Comes out to be the exact same thing. So what does that tell us? Does it matter whether we use the left hand as the height or the right hand as the height? It does not. It does not. At least if you're making infinitely many rectangles. Now, if you're not making infinitely many rectangles, we've seen that it absolutely makes a difference, right? But if we're not, everything is fine. Okay. I don't know where this question was going to. I don't feel like that's in the right place. So I'm just going to cross it out. Oh, I know what it says. That's what it says. So, this is actually a really good question. I'm glad I recognized what was going on here. Let me move this. So what can we say about S? What is the area of S? Well, let's review what we have. We know that L and R are lower bound and upper bound on S. Everybody agree with that? And we know the limit as n approaches infinity of L is equal to the limit as n approaches infinity of R, which was all 1/3. Right? What is this the conditions for? This is the squeeze theorem. So what is this going to tell us? And since the area of S is going to be the same no matter how many subintervals you divide S into, so what we've just done is we've cooked up a technique we can use to calculate the area of any shape where one end of it is defined by a function, right? We just need to divide into infinitely many rectangles and calculate the area of those rectangles. Now, where's the catch that's going to be that we got lucky with because our function was x squared? Right? If our function is an x squared, we're not going to get that nice formula to fall out of it. As we go on through this chapter, we're going to talk about how to get that. But right now, that's purely an artifact of, because Mr. Kulik chose a nice example function that we can use a sequence formula on that we already knew, or a series formula on that we already knew, that we can get this to work out to be a specific number. In general, it's not true. But what could you do to get a really good approximation? Just break it into like 10,000 rectangles, and it's probably going to be good enough, right? Everybody kind of see what we're saying? All right. So again, the idea here now is let's generalize what we've just worked out, right? So let's, instead of talking about a specific f of x equal to x squared, I'm just going to talk about a general f of x. And instead of talking about it on the interval from 0 to 1, I'm going to talk about it on any interval from a to b. And just talk about how the notation kind of changes and the formula changes a little bit now that we're operating in a little bit more generally. So let's say we're going to make n subdivisions. So we split this up into n pieces. So each of these bases we're going to call delta x. In physics, what's delta stand for? Change. So the change in x, so that's basically the base of our rectangle that we're going to be building, is just going to be the total distance from b to a, so b minus a, divided by the number of subdivisions, which would be n, right? If something is 10 units long and we divide it into 20 pieces, each of those pieces is 1/2, right? That's all we're saying. So our subintervals then would be x0, which is a, to x1, x1 to x2, x2 to x3, xn minus 1 to xn, which is also b, right? So those are just the names of the subintervals that we're going to give them. Now, here's the nice part about how we've divided these subintervals. Since these subintervals are all equal size, I know that x1 is just a plus a delta x. And x2 is going to just be a plus 2 delta x's. And x3 is going to be a plus 3 delta x's, right? Or we added one of those to a to get to x1. We add 2 of those to get to x2. We add 3 of those to get to x3. Everybody kind of see what the notation is here? Okay. So our formula then for the sum of our rectangles is going to be f of x1 times delta x plus f of x2 times delta x all the way out to f of xn times delta x. So that's our formula. Again, where the heights of my rectangles are just my f of x's, and the bases are my delta x's. And since the rectangles are all equal widths, the delta x is constant. The heights are going to be changing, but they're just going to be based on the right-hand interval of our rectangles. So, this is like h1, h2, h3 for the heights. It's like b1, b2, b3. Everybody feel okay with what we're doing? Now, if we're doing this with finitely many, we're getting an approximation. That's all we're going to be doing in 5.1 is just approximations, which is fine. And as we remember that the right-hand approximation is going to be an overestimate, or was an overestimate for x squared, will always be an overestimate. No, very good. What's this? When would it be an underestimate?
If it was so it was always an overestimate. But x was always moving in one direction. So it was always overlapping on one side, but if it changed direction, it was going in a different direction.
Yeah, it's the concavity, right? So because this was concave up, when we do the right hand, you're going to get an overestimate because the right hand side is going to be lower or higher than the left hand side. But if you use something that's concave down, now I guess that's not what I meant. I meant just decreasing, right? So if we do this, here the right hand side is lower than the left hand side. So just if you're decreasing. Everybody's cool? So here are the two formulas for the area based on the right-hand rectangles or left-hand rectangles. This is just copied straight from the textbook. All right. So a little bit of notation here that's going to kind of work in, because this kind of stinks to write out every single time, right? It's a lot of writing. You should recognize that as a sum, right? So using summation notation or sigma notation is going to be a way to conserve space on your sheet of paper. Are you required to use that? No. But if Mr. Kulik writes something in sigma notation, should you be able to interpret what he's written? Yes. So just to remind yourself, so if I have the sum of I equals 1 to n of f of xi times delta x, that is the same thing as what we've written there for Rn. Oops. Oh boy. Stop. All right. You behave. Where did... There it is. I knew it was hiding here somewhere. I'll be right back with you. Okay, there we go. Okay. So again, when you're reading a sigma notation, this is just your decoder ring for how you interpret the information there. So the top of your sigma tells you that where it stops, the value that it stops at. And the bottom of the sigma tells you the value that it starts with, and the I equals tells you the summation variable, the index variable. So it says the i's are what are going to be changing. And then inside there is telling you what does each term look like. So this would be f of x1 times delta x plus f of x2 times, it would be, in this case it would be f of xm times delta x plus f of x m plus 1 times delta x plus f of x m plus 2 times delta x all the way out to f of x n times delta x. All right. So let's just look at a couple of examples. Again, this first section was heavy theoretical, right? We haven't really done anything computational to this point, but that's okay. So it says, let A be the area of the region that lies under the graph of f of x equal e to the negative x between x equals 0 and 2. Using right endpoints, find an expression for A as a limit. Do not evaluate the limit. Okay? So first thing I would do is calculate my delta x. So remember, delta x is b minus a divided by n. So what is the b in this case going to be? 2, the end point for my interval, and the a is 0, and the n is just going to stay n. It doesn't tell us how many subdivisions we're building. And in fact, if we want the actual area, how many subdivisions do we need to use? Infinitely many. So we're just going to leave it as an n there. So what do we say here then? Let's talk about what our Rn is. So that's going to be f of x1 delta x plus f of x2 delta x plus f of x all the way out to f of xn times delta x. Okay. But we can do a little bit better than this because we know what f of x is. It's e to the negative x. Everybody's okay here? Now remember, delta x is 2 over n. What's x1 going to equal? Well, it's a plus delta x, right? So 2 over n. What's x2 equal? A plus 2 delta x's, so 0 plus 4 over n. And at this point, do you see the pattern? What's x3 going to be? 6 over n. Everybody happy? So we're going to have e to the negative 2 over n times 2 over n plus e to the negative 4 over n times 2 over n plus dot 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 e to the negative it'll be n times, so that'd just be negative 2n over n times 2n. Oh boy. Okay. So my area then is going to be the limit as n approaches infinity of that stuff. And in fact, let's make our lives easier, right? Just factor that 2 over n out. Or what else, what other way could you write that? Or I could write it that way. They mean the same thing. Either would be correct, whether you use sigma notation or you just write it as a sum. Both would be okay. Again, what I'm looking at when I'm doing that is the only thing that's changing is that exponent, or the numerator and the fraction, the exponent. So I know that's where the I is going to go. And they're just even numbers, right? They're 2, 4, 6, 2n. Everybody's cool? How I did that? Again, you don't need to write it that way for me. It's just an equivalent answer. They mean the same thing. Okay, it's, part B says estimate the area by taking the sample points to be midpoints and using 4 subintervals and then 10 subintervals. Okay. So we'll do 4 first. What's the tricky part here going to be? That our rectangles, the heights are using the midpoint on our interval. So let's just kind of compute some stuff out. Our delta x is 1/2. So my subintervals are 0 to 1/2, 1/2 to 1, 1 to 3/2, and then 3/2 to 2. What's the midpoint in that first interval? What's halfway between 0 and 1/2? 1/4, right? How about in the next interval? What's the midpoint between 1/2 and 1? 3/4. And the midpoint here between 1 and 1.5? 1 1/4, 5/4. And then the midpoint between 1.5 and 2 is 1.75 or 7/4. Everybody's cool? So my area is going to be approximately f of 1/4 times 1/2 plus f of 3/4 times 1/2 plus f of 5/4 times 1/2 plus f of 7/4 times 1/2. All right, let's see if we can come up with a clever way to get this into our calculator so that we don't have to type this in too terribly. So I'm going to type my function into the y equals menu. And I'm going to designate the variable a, and I'm going to store that as 1/2, which is my delta x. Oh. Okay, I didn't like that. Maybe I'll store it as 0.5. Didn't like that. Oh, I know. Okay. I see. We'll take 0.5 and store that to a. There we go. Okay. So what I'm going to do is I'm going to do then vars y vars function y1 of 0 plus I'll do 1/4 plus 0 times a times a, and then I'll do plus, so that's my first rectangle, and then I'll just retrieve that last thing I did and update the 0 to be 1, and then I'll add that to the last thing I did and update that 1 to be 2, and then I'll add that and update that 2 to be 3, and so that's 4 subintervals. Everybody okay with that? Notice that, did I really need to compute each individual midpoint when I typed into my calculator? No, man. I just needed that very first midpoint for the first interval, and then I'm just adding my delta x to each, that many delta x's for each, to each spot. I think we're out of time here, so we're going to stop. You guys should have some homework problems here, though, and I didn't think about that. So let's do just a couple, because this can be like mega tedious. So 5 looks like a good one. Let's do 13. That looks like a good one. Let's do 17. And then maybe like 19. You guys think? Seem good?
Yep, yep.
I like it. See you guys later. I'll get that up onto My Notre Dame also. You're welcome. Have a good start to your semester.